This video is to show how an op-amp can be used as a low-pass filter. So first of all, just some review material from your circuit theory class that, one example of a low-pass filter where an op-amp is not used, it's just a simple RC circuit where if you connect a resistor and capacitor like you see here and you find out what the ratio of V out to VI is, the magnitude of that, you see it comes out to this expression here. Okay, 1 over the square root of 1 plus omega CR squared. And if you plot this out, the magnitude of V out over VI versus the source frequency omega, well, you get this, classic lazy S kind of curve that's a low-pass filter frequency response curve. So this was covered in your 201 class. There's also bandpass filters and high-pass filters, and you can make any of these filters with an op-amp, but in this class, just again due to time constraints, we're just going to focus on one, and that's the low-pass filter. Also remember that where the magnitude equals 1 over root 2, okay, your max is 1 here, and that happens at the lowest frequency possible, which is DC and omega equal to 0. Right, if you have a DC source where omega is equal to 0, well then your magnitude is just, the ratio of V out to VI is just equal to 1, and the magnitude of V out equals the magnitude of VI, and that's the largest the output can ever be in this type of filter, is that the output can just be equal to the input voltage. It can't be any greater. Excuse me. So your max is 1, but if you come down 0.707, which is 1 over root 2, and you find the frequency that corresponds to that magnitude, well, that's called your cutoff frequency, and it's just equal to 1 over RC. Okay, if you were to plug in for omega here, 1 over RC, this term here would equal 1 squared, which is 1, and you'd get 1 over root 2, which is shown on the plot here as the magnitude. And this cutoff frequency, it defines your bandwidth. Your bandwidth for a low-pass filter just goes from 0, the minimum frequency, to the cutoff frequency. And we say that these frequencies within the bandwidth are passed by the filter, where these frequencies outside the bandwidth are not passed. So all these frequencies here greater than the cutoff would be not passed. Okay, so that's just a little review of a low-pass filter from circuits, and this type of filter is called a passive filter, where passive here just refers to that V out can only be as large as VI. It can't be any bigger than that, and that happens at omega equal to 0 for this passive low-pass filter. Now, with op-amps, you can make what's called an active filter, and you'll see that here in an active filter, with this op-amp, it's possible to have an output greater, the magnitude of the output can be greater than the magnitude of the input, and that's due to this op-amp that has transistors inside, like we talked about, that have the ability to amplify. So here's how you make a low-pass filter with an op-amp. Notice that in the feedback you have a capacitor and a resistor. The first time we've seen both components in the feedback. We've seen previous op-amp circuits where you just had a resistor, or in the case where we just had a capacitor, it performed integration. And you can see here that the input is shown as an AC source, where the range of frequencies here can be 0 out to infinity. Okay, so again, when omega is equal to 0, that would be achieved with a DC source, as we've talked about before. Now, we could, to come up with V out versus the input Vs, an expression for that ratio of those two voltages, we could do a node voltage expression right here at node A, like we've been doing in previous op-amp analysis. However, just to make the analysis a little simpler and also to take advantage of some things we already know, when we analyze this low-pass filter, we're going to represent the resistor over here on the input side as just an impedance ZS, and we're going to represent the capacitor and the resistor in parallel in the feedback as an impedance ZF. And when we write the circuit like this, well, look what we have. We have an inverting amplifier, right? Because you see how the non-inverting input is grounded, just like when we did the inverting amplifier, our very first op-amp circuit analysis way back a few videos ago. And you may recall that when we did the node voltage expression here and solved for V out over V in, well, it came out to the ratio of these, it came out to the ratio of two resistors with a negative sign that indicated the inversion, the 180-degree phase shift between V out and V in. Well, you see here, when we represent the low-pass filter like this with impedances, and remembering from your circuit theory that we treat impedances just like resistances. In fact, remember, impedance has units of ohms just like resistance does. Well, it should make sense to you that we can just jump to that V out over the input Vs for this circuit here would just be minus the impedance in the feedback divided by the impedance at the input. So the only difference here is we have impedance instead of resistance. But again, we treat impedance just like resistance because they have the same units as you did, or what you first learned in your circuit theory. Okay, so really we're just treating the low-pass filter as an inverting amplifier with impedances instead of resistances. But we're not done. We can now get this expression for V out over Vs in terms of resistance and capacitance by remembering from our circuit theory that the impedance of a resistor is just its resistance, and impedance of a capacitor is minus J 1 over omega C. So now Zs, well, that's just a resistor, so it's just going to be equal to the resistance Rs. Zf is going to be the impedance of the resistor in the feedback, Rf, in parallel with the impedance of the capacitor. So the minus J 1 over omega C, where this C is Cf because we have it Cf in our diagram. So we have what the impedance of Zs is. It's just Rs. Okay, now to get Zf, we just have to do either product over sum or sum of reciprocals with these two impedances here. And I chose to do sum of reciprocals reciprocated. So that's just going to be 1 over Rf. And then when we flip the impedance of the capacitor, we're going to get plus J omega Cf. Okay, so this is sum of reciprocals. And then this whole thing is reciprocated. Okay, and then finally, just to clean this up a little bit, okay, we're going to take this expression and just multiply through top and bottom by Rf. So we get Rf divided by 1 plus J omega Rf Cf. Okay, and now V out over Vs is just going to be minus Rf divided by Rs, and then divided by the same denominator, 1 plus J omega Rf Cf. And now, if we take the magnitude okay, magnitude of a quotient is just the magnitude of the numerator divided by the magnitude of the denominator. So magnitude of minus Rf over Rs is just Rf divided by Rs. Okay, and the magnitude of a complex number is just sum of the square rooted. So we got a square root. And then we'll have 1 plus, oops, that tick ignore, that's just a mistake with the pen here. So we got omega Cf Rf. Alright, so you see here's our expression for the magnitude of the ratio of V out to V in, where V in is Vs. We'll compare that to what we had with our passive low-pass filter from our circuit theory, and you can see what's different is that instead of 1, just 1 in the numerator, we have the ratio RF to RS. So that means that when omega is equal to 0, okay, when we get our peak magnitude, when omega is equal to 0, well, it's determined by the ratio of the resistors. So we can get a greater output voltage than what we have at the input by setting the ratio of these resistors to greater than 1. And if you look at our circuit diagram again, and remember that when we have a DC frequency, when omega is equal to 0, capacitors to DC act like opens. So when omega is equal to 0, it's as though this capacitor goes away, that it acts like an open, and then you're left with just RF in the feedback, and look, that reduces to a basic inverting amplifier. Okay, so this low pass filter, when omega is equal to 0, it just becomes an inverting amplifier, and your output and your input are just related through the ratio of the two resistors. And again, if you make that ratio greater than 1, you're going to have a larger output than what you have at the input. So what occurs here is that with the active low pass filter, you end up with, let's straighten this out here. Oop, there we go. Okay, so what occurs here with the active low pass filters, you get the same type of frequency response curve. Okay, so this is V out over Vs magnitude, right? So versus source frequency, you're going to end up with the same lazy ass kind of curve, okay, just like in the passive case. But now this peak is determined by the ratio of the two resistors. Oops, this is RS. Okay, so this peak is determined by the ratio of RF to RS. Actually, let's fix that. Make this clearer here. Okay, so this is RS here. Okay, and then if you come down to RF divided by RS all over root 2. Okay, if the magnitude is your peak divided by root 2, well, the frequency that corresponds with that, again, is the cutoff, just like in the passive case. Okay, and that determines your bandwidth. Okay, your bandwidth is still from 0 to the cutoff, just like in the passive case. And then to get a magnitude of RF over RS over root 2, in other words, in order for this denominator to be root 2, well, omega would have to equal 1 over CF RF. And you see that's your cutoff frequency equation. Just like in the passive case, it was 1 over RC. Okay, right here. In the active case, it's still 1 over RC. It's just that we're using subscripts F and R. So it's the R and the C that are in the feedback that determine where your cutoff frequency is. So as you can see, this active low-pass filter, it's essentially what we had in the passive case. However, the big difference in what the term active means is that it is possible to get an output voltage that's greater than the input voltage by, again, making the ratio of these two resistors greater than 1. Now, as I mentioned, in this class we only cover the low pass case. If you're interested in more detail about the high pass, active high pass filter and also active band pass filter, well, I'll refer you to the text. There's a discussion in the text about those filters.